Hello everyone. Hope you're all doing well. Hope you all had a good weekend. But today we're going to jump on into one of my favorite units in math. As I'm sure you've all read by now, it's on conic sections. It's a really great unit because there's a lot of practical application for conic sections outside of school. So as we go through this, just a reminder, you're taking your Cornell notes, you're writing down your questions so that you can either review your notes and try to figure out the answers, or you can ask me the questions later if you need to. Lastly, before we begin, we're not going to be covering too much of the actual math behind the conic sections today, because I really just want to hammer home what a conic section is, what they are, and the application for them. So that way when we do get to the math, you guys have a very strong foundation of what they are and how they can be applied. So, our agenda for today. First, we're going to start out with describing what a conic section is. We're then going to go into what the different conic sections are. And then we're going to finish it up with looking at the differences in conic sections and how they appear in our everyday lives. So the bleeding question I'm sure you guys all have now is, what is a conic section? Well, we start here. This image over here on your right, this weird looking thing over here, is what is called an infinite cone or a double-sided cone. We are working with a three-dimensional cone, as you guys can see from the 1, 2, 3 red lines indicating the 3 dimensions. And this one right here is the axis of the cone. This cone is essentially expanding outward along that axis infinitely. So now that we know what our weird looking double-sided ice cream cone thing is, what we're going to do today is we're going to imagine we have a very flat plane, like a sheet of paper, and we are going to cut across this cone in a bunch of different orientations. And what that will do is it will create a bunch of unique shapes for us. And these 2D images that we're going to create when we cut it, these are what are called conic sections. So a conic section is a shape formed between an intersection of a plane and a cone, and the 2D image of this intersection results in the shapes of the specific conic sections. So today we're going to set this infinite cone, we're going to set it on a cutting board, and we're going to make some chops through it, and we're going to see what kind of cool shapes we can create. So the very first one that we can is a circle. Now I'm sure pretty much everybody in here could tell me what a circle is, but it's a round enclosed curve where all points are an equal distance from a center. So circles are everywhere, they make the world go round. I'm sure you're all pretty much familiar with what it is, but we're interested in how do we form this circle from a cone. So over here on the right, we have our double-sided cone again, and we have this little pink square. This is, like I was saying, it's our plane. It's like our sheet of paper that we're sliding across this cone. And we're going to intersect the cone with this plane that is perfectly parallel to the base of the cone. So this plane right here is perfectly parallel to the base of the cone. And what that's going to do for us is it's going to allow us to create a perfect circle. Now, this only works when the plane is, once again, perfectly parallel to the base. Because if the plane is slightly askew, we end up with what is called an ellipse. So an ellipse, I'm sure some of you have seen a shape like this before, and you've most likely called it an oval if you're not familiar with what an ellipse is, but they're not quite the same thing. So we're not going to refer to these as ovals in this class. We're going to refer to them as ellipses, the more mathematical term. A rounded enclosed curve where the lengths of the axes are not necessarily the same. And what I mean by that, the lengths of the axes are not necessarily the same. If we imagine there's a small line that runs from the point here to the point here, and another one that runs from here to here, the two high and low points and the left and right points. These are what will be our axes. This is one axis, and this is the other. And when those two lengths are not the same, we end up with this oblong shape right here this ellipse. If those two axes are the same, we end up with what we just looked at, a circle. So because this plane is intersecting the cone at not parallel to the base like the circle was, but slightly askew, we end up with a longer axis in one direction. And that is going to result in these shapes right here, which are called ellipses. So now, I know you guys are all dying to know, okay, we've looked at a flat plane, we've looked at a plane that's slightly tilted, but what if we keep tilting it? Well, if we keep tilting it, eventually this plane is going to intersect the base of the cone. And that happens when the plane is exactly parallel to the edge of the cone right here. So if you look at this line right here, if we all remember the slope, how steep a line is, right? And we look at the same slope of the plane, we can see that they're parallel. And this results in this cool shape we have right here, which is called a parabola. And this only occurs, like I said, when this plane is exactly parallel to the side of the cone. Because if the plane is a little bit less steep, we end up with an ellipse. And if it's a bit more steep, we end up with the plane intersecting both the top and bottom of the cone, which is our next shape, a hyperbola. Now, the hyperbola is kind of the odd one out of the four conic sections, as you may have noticed, because it's the only one that has two lines in each graph. And this is because, as I mentioned, it intersects both the top and the bottom cone. But one thing that separates the hyperbola and the parabola, because these are not just two hyperbolas these are not just two parabolas back to back, is, as you may or may not have noticed, the parabola, if you look at it, as we increase further and further to the right, it gets steeper and steeper and steeper and steeper, and eventually these two lines, they won't get parallel, but they want to reach parallel to each other. Same thing over here. As we go further and further, this is getting flatter and flatter and flatter and flatter. If we look at the hyperbolas, these aren't doing that. These are essentially reaching toward what these X-shaped lines are. These are called asymptotes. An asymptote is just a line that the graph approaches but will never reach. So instead of these curves functioning like parabolas and going more and more and more and more vertical, instead these graphs, they try to reach where these lines are, but they never actually reach them. So it's essentially a straight line, a curve, and then a straight line. So we have now looked at the four different conic sections. We know all about what they are, kind of what they look like, how they're formed from the different cuts on the cone. So we're just going to go through a little bit of review here. These are going to be questions on Edpuzzle. So make sure you guys are selecting your response there. You have to hit submit before the video will continue. So the very first one we're going to look at is, what is a conic section? Now, a conic section is the shape formed from the intersection of a plane and a cone. So as you can see here, we have our cone. We really only have half the cone here, remember, because it's a double-sided cone. But we only have one half of it here, and we have a plane. We have a plane that is intersecting this cone and forming this shape, which is called a conic section. Now our next question is going to be, what are the four conic sections? Hopefully you guys all got this one right. It is, we have our circle, we have our ellipse, we have our parabola, and we have our hyperbola. And as you can see here, once again, these are the different orientations of the planes that intersect the cone to form the different shapes: circle, ellipse, parabola, and hyperbola. Now, I'm an engineer, so whenever I learn something, I really love to know why. Why do I care? Why do I need to know? And that's because these these conic sections are very useful everywhere in life. I'm sure you can look around your room right now and you can find an example of one, most likely a circle, just by looking around your room. So if we can study and understand the math behind these different conic sections, we can understand much more about how the world works. So we're going to take a look at some examples and kind of just think about how knowing the math behind them could help us understand some things. So first and foremost, circles. For example, circles are used in the design of, let's say, Ferris wheels, gears, and mechanisms. So if these gears were not circular but instead a different shape, it would be very, very difficult, if at all possible, to get all the cogs on the gears to line up and for the gears to function properly. So if we can understand circles and the math behind them, we can get these gears and more complicated mechanisms to function more efficiently. Same thing with tires. Could you imagine if your tires were elliptical? That wouldn't be a very fun ride. Finding the epicenter of an earthquake. So some of you may not be familiar with earthquake science, and that's perfectly fine. But over here, just a quick little brief crash course. If we have a seismograph, the instrument that detects vibrations from an earthquake, they can only detect how far the earthquake is. They can't detect location or direction. So if we detect an earthquake here at Minneapolis, and it gives us a distance, we only know it's somewhere on this circle. Same thing with Detroit. We only know it's somewhere on this red circle. And lastly, same thing with Charleston. We only know it's somewhere on this circle. Because once again, those machines, they can only detect how far it is, not location. So understanding that a circle is all points that are equal distance from a center, we can use all three of these to pinpoint a location and find out exactly where the epicenter of the earthquake is. So there's just a little bit of practical application for circles. Next we have ellipses, and these are very easy to pinpoint examples out in space. So planets, comets, satellites, they all revolve, they have elliptical orbits for the most part. There are different orbits which we will talk about in a sec, but the elliptical orbit is a very common orbit between, like I said, planets, comets, and satellites. So if we can understand the difference in orbits and understand the math behind ellipses, we can get satellites into space more effectively, and we can calculate where the planets are going to be and the trajectories of the planets. For parabolas, the most a lot of parabolas show up in physics and engineering based concepts. So the most common one would be gravity. So if we throw a ball up in the air, it's going to slowly slow down, and then it's going to reach its maximum point, and then it's going to slowly start falling and get faster and faster and faster until it reaches the ground, effectively forming the shape of a parabola. And as we'll find out later, this also reflects the equation for gravity, which is parabolic. Satellite dishes as well, they have a parabolic shape so that they can focus all the waves that are coming in to a single point. Suspension bridges, they have parabolic shapes so that they can more evenly distribute the loads from the bridges. And then lastly, we have hyperbolas. Over here on the right, you can see this is what is called a hyperbolic trajectory. It's not an orbit, kind of like the ellipse was, because this happens most likely once in the body's lifetime, because it's going so fast that it can't be caught in an orbit. It's going so fast, it's screaming, and then it gets to here, it gets affected by the gravity of Earth, and then it just gets shot off in one direction again. This is just like the graphs of the parabolas. You have a straight line, then you have the curve, and then you have another straight line. It's called a hyperbolic trajectory. So if we can calculate those, we can calculate comet flybys, when those are going to be, how close they'll get to Earth, all that stuff. And then my favorite application of a hyperbola over here, because as you know I worked with airplanes, sonic booms. So for those of you who are unfamiliar with what a sonic boom is, basically when you're going faster than the speed of sound, you're going to create a shock wave behind you, and it's going to emanate out in the shape of a cone from that single point all the way out in waves. Okay, so if we are flying parallel to the ground, just like in this image here, eventually as this cone emanates out, the ground is going to kind of slice it like our paper was in the example. It's going to slice that cone, and it's going to form half of a hyperbola right here. And this is interesting because every single point on that hyperbola experiences the sonic boom at the exact same time. So this is something we want to know because we want to know who exactly is going to hear the sonic boom and at what times they're going to hear it. So if we know the math behind the hyperbola, we can calculate that and calculate what that zone of a sonic boom is going to be. So now you all love math, you all love conic sections. We've gone over what they are. We've gone over the different applications of them. We know them by heart. We're going to do awesome in this unit. But I can't leave you without an assignment. So I want you, it's not going to be hard, but it's going to require you to think just a little bit. I want you to think of a real-world example of a conic section. Be it a circle, an ellipse, a parabola, or a hyperbola. Just some real-world example. I know there's plenty of them because we just went over quite a few of them. And then I want you to write 2 to 3 sentences describing why you think knowing the math behind that specific example could help you learn or understand something more deeply. Kind of just like what we were talking about. So for example, planetary orbits take the form of ellipses. If we can calculate the formula for a planet's orbit, we can know mathematically where the planets will be. This will make traveling between them easier in the future. See, so there's an example. I identified a real-world conic section, and then 2 to 3 sentences just describing if we know how to do the math behind it, how can that benefit us? So that's all for me today. That will be due next time we see each other. And if you have any questions, feel free to email me, but that's all I have for now. Thank you.